We're going to talk about families of functions. A family of functions is a group of functions that share similar characteristics graphically and algebraically. Lines are a family. If we think about the lines that we've been dealing with, each line algebraically has a slope and it has a y-intercept, and they can be found within the function in consistent locations. Slope is always in front of the variable. The y-intercept is always the constant. And those values impact the graphical representation consistently. So any two lines, I look at their algebraic rule, I know how the values inside that algebraic rule are going to affect the graph. Okay, so that's what I mean by the graphical representation consistently through all different variations. Quadratics are another family that we'll investigate. They generate parabolas, which you've probably heard in the past. I'm going to pull up an appendix here of functions, families of functions that you would see in throughout a high school curriculum, math curriculum. So here's a list of what we end up calling parent functions, but parent functions generate the families. So we've got our lines that we've been dealing with. We see they're called linear. X to the first is what we call the most basic parent function. We've got our absolute value functions, as we've talked about a little bit. I'm going to skip this one. We won't talk about that one in this class. I've got quadratics, and those create that parabola. Cubics, we might talk about a little bit in this class. Square roots look like this little thing right here. These are cube roots. If you've ever heard of an exponential function, if you've listened to anything about the virus and how it spreads exponentially. This is kind of the graph that represents. Logarithm looks like this. These two things tie together. But these are every root function, every square root function is going to have some type of relationship that looks like this. The graph is going to look something like this, and the rule is going to look something like this. Okay, every exponential, the graph is going to look something like this, and the rule is going to look like this. Okay, so there's those relationships, those characteristics that are shared and they're similar. Let's go back to our notes. Okay, so a parent function, sometimes called the mother function, is the most basic function of a family that exhibits the characteristics or traits that the family shares. So with a line, our parent function for a line is that's the most basic function that we can come up with. It has a slope of 1 and a y-intercept of 0. Okay. For a quadratic, our parent function is x squared. It's the most basic parabola we can come up with. All right. We then go through a series of movements and alterations of these parent functions, and these alterations are called transformations. Okay, the root word there is transform, which means to change. But a transformation is an adjustment to the parent function that generates a member of the family. It says the adjustment or change is made within the function rule and can be recognized, interpreted, and applied graphically. Transformation adjustments are consistent and pattern-based for all families. So if I can learn how a transformation is applied to a line, to get a new line, to get a family member of that function, then the same algebra done to a parabola will generate another member of that parabola family. Okay, so I'll kind of explain it as we see some examples here. But one of there's a series of transformations. There's kind of go through them. I'll list them here real quick for you. There are what we call translations, which basically means we're going to move these things left, right, or up and down. Okay, that's what translation means. It's just a slide. If you remember back to geometry, you might have done things called slides or glides or something like that. They're the same thing here, but instead of doing it with like triangles or squares or rectangles, we're doing it with these curves. We have translations. We have sometimes they're called shifts. Sometimes. So shifts. So we have translations. We also have reflections. We have what we call stretches and compressions. If you remember to geometry, those were called dilations. It's the same concept, just we use different terminology. And right now, I believe that's going to be really the only ones that we really talk about for the most part. Okay. We'll go through a series of different relations here and different ways of communicating these transformations through our algebra. Okay. So the first one we talk about is a vertical translation. A vertical translation. So vertical means up and down. Okay. And simply by definition, a vertical shift of a parent function. So the notation of this is that, and this f of x is whatever our function is. So if our function is the line x, then that would just be x. If it's x squared, if it's the parabola, then this would be x squared. This might be x cubed, might be square root of x, but all it is some function. Okay, we don't care what it is because adding some amount k to any function is going to do the same thing to that function. Okay, so I'll explain that with a Desmos or GeoGebra application here in a minute. So if I take my function and I just add k to it, what that's going to do, because I'm adding, it's going to move it up. It's going to take my function, whatever this was, and it's just going to slide it or shift it this many units up on my graph. Minus k, same concept, but instead of moving up, it's going to move down. So I kind of want to investigate this two different ways here. First thing I'm going to do is just create a table here of values for this function here. So I'll say x and f of x. Now I'm just going to use a couple maybe key points. If I go like -2 and plug that in here, I should get -4. If I plug in -1, I should get -2. 0 is going to give me 0. 1 will give me 2, and 2 will give me 4. Okay, so that's kind of Algebra 1 where we learn how to graph these things. If we want to graph this, obviously we go 0, 0. Let me zoom in here a little bit so I can graph it a little bit more precisely. 0, 0. We got 2, 4. 1, 2. We got all these points here. So we got those points that we can graph. Alright, so we've got that graph there from what we've been doing for the last couple days. Okay, now we come over here to this one where we've got, make another table, x and f of x, and I'm going to use the same x values, -2, -1, 0, 1, and 2. And now if I put -2 in here, I'm going to get -4 plus 3, so -4 plus 3, which equals -1. If I plug -1 in, I'm going to get -2 plus 3, which equals +1. Plug 0 in, I'm going to get 0 plus 3, which is equal to 3. If I plug in 1, I'm going to get 2 plus 3, which equals 5. If I plug in 2, I get 4 plus 3, which equals 7. So now the ordered pairs I would graph would be -2, -1, -1, 1. I'll plot those ordered pairs. So I'm going to go down and do that. So -2, -1, -1, 1, 0, 3, 1, 5, and 2, 7. This headline says replacing RBG with a woman like Amy Coney Barrett is beyond tokenism, it's an affront. She said if the president succeeds in appointing such a staunch opponent of reproductive rights to the court, he'll advance his own agenda of turning women's rights back 50 years. Appointing Barrett could well result in overturning Roe v. Wade and the... Alright, so what we see here then is that these two lines are very similar to one another. Okay. And the way that this line here is actually generated is if I know what 2x looks like, then all this plus 3, I said that when we add, it's that plus, that's the plus k. So the f of x is the, this is f of x here, so this would be f of x plus k. To go from my 2x, if I were to take each one of these points on here and shift it up 3 units, so that point shifted up 3 units, would go right there, which is that point right there. If I take this point and shift it up 3 units, it would go right there, which matches that point there. This one shifted up 3 units would go right there, which matches to this point here. This one up 3 units goes there, which I've got graphed right there. And this one up 3 units would match up to that one there. So the idea is, if I know what 2x looks like, and I know what the ordered pairs are on 2x, and I automatically know what the ordered pairs are and what their line looks like for 2x plus 3, because 2x plus 3 is simply this black line of 2x. Every single point lifted or shifted vertically 3 units. Okay, so we can see then this concept a little bit in GeoGebra. So this is for another class, so let me clean this out. Alright, so if I've got some function f of x, I'm just going to call it x, okay, could be 2x, could be 3x, could be 4x, doesn't matter, but now if I say f of x and I add some a amount to it, actually let's call it k, so k was what our rule was saying, okay. You can see here, what it does is it creates what we call a slider here in GeoGebra. But what it's doing is saying, okay, if I had this point right here, and let's just use maybe that point right there on the red line. Okay, I just took a minute to pause this and generate this so you can see it a little bit better, a little bit easier of a conclusion here. So right now I've got my parent function x, okay, but I'm going to add some k to it, okay. Now that k value, what I'm going to do right now is I'm just going to make it 1. So you can see that the parent function was x, now the member of the family is x plus 1, and you can see then that, and I've just used this point A right here and this point B as just 2 arbitrary points, but it could be, they could be anywhere. I can move them anywhere I want to. So this is going to be true, but I chose those 2 because they were convenient x and y values. Okay, they're whole numbers. But you can see then that what this does when I have x plus 1, all it does is takes this red line and shifts it up 1 unit. But what it really does is it takes every ordered pair that's on this red line and it adds 1 to the y value. If I look at this point of A compared to this point of C, they match, they're corresponding, but the y value of A, add 1 to it, and you get that y value of 0 for C. Same thing here. If I look at the y value for B, which is on the red line, add 1 to it, and I should get the y value of D on that green line. And you can see then that as I start to increase K, all that's doing is it's taking that red line and shifting it up K units to now get the green line. Okay? And you're seeing that these dotted blue lines, all I'm doing is trying to show you that the distance that is separating these two lines now is that plus 5 that we were adding to that function. Okay, we can also go the other direction. So if I want to go down, I want to shift this thing down. Now you see that if I shift down, I'm subtracting 4. So that means this point here and that point there have a y value that differ by 4. This was a y value of -1. This one down here is a y value of -5. But when we do a vertical shift, all we're doing is we're adding to the end of the function some amount that we want to move it up or down. Okay, so now all I've done is instead of looking at the equation or the function y equals x or f of x equals x, now I'm looking at the quadratic x squared. And if I take my k value and I start to increase it, so make it do something like this, let's make it go up to 3. You see how that makes the rule over here. But my hope was that you also saw that all I've done to get this green graph, which is x squared plus 3, all I did is I knew what the red graph looked like, x squared, and I took every single point and I moved it up 3 units. And that's kind of what you're seeing here with this point A and this point C. -1, 1 was on the red curve on the parent function. Add 3 to that y value and you get a point that is on the green one. Now that point, no matter where it's at, let's put it here. Another good point on the red parabola is -2, 4. If I add 3 to that y value, shift that thing up 3 units, you're seeing that C to A is 3 units. That distance right there, that's 3 units, that dotted line. And you see that 4 plus 3 gives me that 7. So moving that thing up and down, so if I move it up by adding a number to the end of it, and I move it down or shift it down by subtracting. Okay, so this point here is that point there translated or shifted down 5 units. And all of these points do that. Maybe another way of kind of visualizing this is, let's say that I have, let's see if I can hide. Okay, so right now I've just got x squared being shown, but if I were to take and say, okay, I'm going to take x squared and subtract 4 from it, what would that look like? Well, I'm going to move this point here, and what I'm going to do is I'm going to keep this segment attached to it, so there's going to be basically it's like a paintbrush that is, I know, a distance of 4 units long. And as I move this point, you can kind of see that paintbrush is going to trace something that is 4 units away from wherever that point is on the parent function. So I get that parabola there, and that parabola is 4 units below that parabola, so it's x squared minus 4. Let me see if I can put a different function in here for a moment. Okay, so this is a function. This is called the square root function. Okay, so again, square root of x is the parent function. If I start to add a number to that, so let's add 2 to it, you see that a point that was on the parent function gets shifted up 2 units to there. Okay, this point right here gets shifted up 2 units and becomes that point. Okay, so all those points between those two graphs are 2 units apart from one another, and all I've done is taken essentially that one and slid it up 2 units. And you can see that up 2 units right here in the way we define that g of x function. If I want to go down, I go down. So that is an explanation, hopefully a pretty good understanding now of vertical movements for functions. Okay. Now the other type of translation that we have is horizontal. So horizontal translations are hard to see with lines. Okay, so I'm not going to deal with lines right now with you. We're gonna jump straight into working with quadratics. But what a horizontal translation is, same definition. It's a horizontal, which is left or right, shift of a parent function. The notation that we're going to see is this. This is kind of a little bit different. Okay, notice the last time it was vertical, it was f of x plus k. That was vertical. Now horizontal, you see that you add the k to the x inside these parentheses. So I'll kind of demonstrate what that looks like when we get down to a specific quadratic. Now here's where it gets kind of confusing. And I'm not going to get into the details right now. Maybe if we have time later on, maybe when I get back to class next week, we'll explain this a little bit more. But if it's plus k, this actually is a movement left, which is counterintuitive to what you would think. I think most people see plus and think move right, but with a translation, if you're adding to this x before you apply the function, you're going to actually move opposite of what that sign is, or what you'd think you would move with that sign. So that's moving left. If it's minus k, that is moving right. Okay. Now I said that you're going to substitute, or not substitute. You're gonna add k to x before you run that value through the function. So I'm going to kind of give you a scenario here, and it's because of order of operations. Okay, if we were going to come down here and do, again, the chart, x and what f of x would look like, for the parent function x squared, we would start with maybe -2, square that, you get 4, -1, you get 1, 0, 0, 1, 1, and 2, 4. Now over here, what we're going to get, if I try the same value, -2, now order of operations says you put that -2 in and you add 3 to it before you square it. So order of operations says that's going to be 1, and then I'll square that 1. Okay? So if you have to add to your x, which is what I'm doing here, I'm adding 3 to my x of -2 before I actually conduct the overall function, which is squaring. That is going to be a left or right movement, and that process is why moving or adding here moves it to the left and subtracting moves it to the right. So I'll try -1 again. Okay, so I'll plug -1 in, add 3 to that, and then square it. So I got to do order of operations first, so that's going to give me -1 plus 3 is 2. So 2 squared would be 4. If I try 0, be 0 plus 3, which would be 3 squared, gives me 9. Try 1. 1 plus 3 squared, 4 squared is equal to 16. And then we'll go 2. And I will get 2 plus 3 squared. So it gives me 5 squared, which is 25. Okay, so I'm going to come over here, and I think it's going to maybe make a little bit more sense. I mean, we can graph this one, but I think the way I've got things set up here, you're going to maybe run into an issue with the graph, but we'll see. If I go x -2, 4. So -2, 4 would be that point there. -1, 1 would be that point there. 0, 0, 1, 1, and 2, 4. Okay. We would also, if I had -3, it'd be -3, 9. And if I had +3, it'd be +3, 9. So I'll let you kind of visualize. I'm not very good at drawing these parabolas with my tablet, but that would be that parabola. Okay, so if I come over here and plot the points, it's -2, 1 now. -2, 1 would be a point. -1, 4 would be a point. 0, 9. Okay. Now I'm going to get like 1/16, so I run out of room up there. So what I was saying is that right now, because of the x values I chose, kind of ran out of room. But let me try -3 here. If I plug -3 in, I'm going to get -3 plus 3, which is 0 squared, which is just 0. So -3, 0. If I try -4, I'd have -4 plus 3 squared, so -1 squared, which is 1, so -4, 1. I'll try one more, -5. -5 plus 3 squared equals -2 squared, which is 4, so -5 will be up at 4. And you can start to see now that I do end up with that parabola right there. And you can kind of visualize, okay, well, if I started with x squared and I move that point at 0, 0 to the left 3 units, does it turn into that point right there? If I move that one 3 units to the left, does it become that point? Move that one 3 units to the left, does it become that one? And do that with all of these points, and you'll see that this x plus 3 squared is this function just shifted 3 units to the left. Alright, so back in GeoGebra, this is the same kind of thing going on here. I've got my parent function, and then I've got the transformation that's going to be right here. Right now they're the same because k is 0. But if I start to move this number to the right here, okay, so k becomes 1, you see that this point here at A, so let me see, we'll just look at these 2 points right here instead of writing them down. You see that they differ by a value of 1, which is that 1 right there. Okay, their x values differ by that 1. If k was 2, we see that ordered pair right there that was -1, 1 now becomes -3, 1 because of the distance of 2, which is seen right there. Now it was plus 2, so that means we move to the left 2. And I can do that same thing that I was doing earlier where I take that point A and I can show you as I move it, okay, it's tracing over. That paintbrush is 2 units long. It's fixed distance. And as I move A along the parent function, it then also traces out that family function, okay, or that member of the family, okay. So that's something to kind of think about as we're doing this, that when I add a number, it moves it to the left, and I think you can see that relationship happening when I do that there, okay. If I were to move, if I wanted to go back to this, now let's say that I subtract a k value from the x before I square it. So it looks something like this. It looks something like this. You can see that that is taking my parent function and moving it then to the right. Okay, so that's kind of the difference between working with vertical and horizontal shifts. So let's go back to, I think one that we used was square root of x. Let's see, if I go square root of x here, you can see then that if I start at 0, and I don't know where my vector went, alright, so if I've got square root of x as my parent function, now if I add an amount to that. You see that it adds now underneath the radical, so I'm adding to x before I square root, just like in the last one I was adding to x before I squared. That is going to move things to the left if I'm adding. So this point right here, let's just look at this point 0, 0. 0, 0 turns into negative 5, 0. This point, like right there, this point right here of 1, 1, move it left 5 units becomes negative 4, 1. This point here, 4, 2, move it left 5 units becomes negative 1, 2. Okay, so that's a relationship that we see now. If I want to move it to the right, so this is my parent function again, I move it to the right 5 units, you see that it's now x minus 5 underneath. And it doesn't have to be 5 units, it could be 4 units, it could be 3 units, it could be even more than 5. Just the way my slider's kind of stuck right now between negative 5 and 5. So that is how we deal with translations. Now, you're going to see from time to time what we call like a generic f of x, generic function. So they'll draw something that looks maybe like this. And all they're looking for here is that it's a function. So it doesn't have to be anything fancy other than that it's got, if you remember functions, it has to pass the vertical line test. So I've got something that looks like this. I'm going to just call that function f of x. And they will ask, okay, well, if that's f of x, what does f of x minus 3 look like? And all that means then is, if this is your function, remember subtracting 3 from the entire function drops it 3 units. So that point right there, all these y values are going to go down 3 units. Okay. Now you can do all of these points, but because it's a segment, if I do this point here down 3 units, and now connect these two red ones, that will effectively move that point down 3 units to right there where it belongs. This one here down 3 units, so 1, 2, 3 would be there. This one down 1, 2, 3 there. And you can see then that we would have that, and this function here would be f of x minus 3. Now let's say that I want to move it to, let's say I do this. Let's go f of x. Now let's say minus 5. And they ask you, well, what does that look like? Well, now I'm subtracting from the x before I do anything. It's in that, it's that associative property with the x. So that tells me I'm moving left and right. And because that's minus, that tells me I'm going to move to the right. So I'm going to take every one of these points and move it 5 units to the right. So 1, 2, 3, 4. Let me erase this so it's not in the way. So I go 1, 2, 3, 4, 5. Move this one 5 units to the right. 1, 2, 3, 4, 5. I'll move this one 5. 1, 2, 3, 4, 5. And we'll move this one 5. 1, 2, 3, 4, 5. And then connect those with segments. And we can see that we have the same looking function. It's just shifted. It's shifted to the right. You see that they overlap. They're the same. Okay. It's just shifted 5 units to the right. Okay. So this red one here is moving up and down, and then the blue one is moving left and right. So that's how we deal with a generic function. I'm going to stop there. We're at 35 minutes. I'll pick up with the reflections and what we call vertical stretches or compressions, or a couple different terminologies that we use, or terms that we use to talk about really the same behavior when we talk about vertical stretches. So we'll get to that in the next video.